In this example, we're going to have a look at how Sallen-Key filter design of a low-pass filter can be implemented by analysing the transfer function and using the TutorTIMS Biquad Laplacian continuous time module. First of all, let's have a look at the mathematics. Here we have a document where I'm discussing filter design in TutorTIMS with the Laplace Biquad. You can download this document for yourself from our website. We'll move quickly through it. Typical Sallen-Key filter. Choose some components. Set the cutoff frequency 1.59 kilohertz. All standard stuff. We end up with some components. We have a look at the traditional transfer function, and then we relate it to the generic transfer function for the biquad, which only has poles and no zeros. Hence, we're only interested in the denominator. So, moving right along, you can see some of the relationships here between the coefficients of the denominator and the coefficients of the more general form, where omega squared, the natural frequency, expressed as an angular frequency, is directly related to the A2 coefficient. And the A1 coefficient is directly related to the Q and the natural frequency. So let's move right along with this critically damped filter. And we notice that the Q was 0.707, so it's maximally flat filter, as can be seen in this plot. And then we enter the component values of your Sallen-Key design. You'll have the actual transfer function, which you can then normalize by dividing by omega 0, and then solve using this traditional quadratic equation to give you the actual poles. Let's have a look at these poles and what they represent. Here we've drawn the poles. They basically are two complex points on the left-hand side of the S-plane. But what they represent are vectors. And if we go back to the transfer function, we can see they represent the product of the distance between the frequency of interest and that pole. So S minus P1, S minus P2. If we have a look down here, S is a point on the J omega axis, and P1 and P2 are the magnitudes to that point. So how would we analyze this? We would come down here to this point. For example, point 0 when at the DC point is the magnitude of the two vectors, which gives A. If the point moves further up the axis to the point B, we then have the magnitude is the product of these two vectors of differing size. And if we do the maths, it comes out to be 0.707, 3 dB down. So that point is the 3 dB point. And if we go way up the axis to point C, we end up with the 40 dB point. This is all just approximations which allow you to see how the pole zeros, the poles in the S-plane can be understood to represent something real, not just to represent a real frequency response of this circuit, not just a bunch of abstract mathematics, although it is that as well. Coming back to this equation, how do the coefficients relate? Okay, so first of all, let's work out the coefficients. The coefficients are up here. Okay. Here we have the poles. From the poles, we can use these formulas to work out the coefficients, and then we can implement them in the transfer function. So let's come here to the transfer function. You'll notice that here we have the coefficient A1 and A2. We're inputting the sine wave, we're inputting noise, and let's look at the spectrum of that noise. Here we are, we're inputting average. We're inputting some broadband noise, which has a bandwidth of 12 kilohertz, and our frequency of interest is down here. 1.59 is the corner frequency we've designed. Here is the output, the blue signal. So let us now look at the frequency response of the blue signal. Okay. You can see it has a roll-off. Let's move in closer. And let us turn off A and B, and let us move these out of the way. Okay, now you can see one point five nine. Now, let's have a look at these relationships here. A1, if A2 is increased, omega 0 is increased because the radius of the circle is increased. Let's try that. If we increase A2, let's double it and see what happens. You'll notice it's now increasing. Increasing A2 has increased the roll-off of this filter. If we come back here, let's have a look at A1. A1 goes down, Q goes up. This is because A1 is the real part of P1. So as the real part of P1 is reduced, the poles move closer to the axis, which makes the contribution smaller, which makes the magnitude larger. Let's try that. A1 is reduced. A1 has been reduced. Let's see what happens here. You'll notice this is starting to become more peaky. Let's reduce it even more. Even more so. What happens if we reduce it even more? So now we're moving the poles very close to the axis, becoming very peaky. Let's reduce it even more. What will happen? We're starting to get oscillation. Let's really go to town here. Oscillation. Look at that. Fantastic. It's almost an oscillator. And if we go back to the original value, back to the original values, you'll see that the system restabilizes once again. So this is now the implementation of a second order Sallen-Key as a Laplacian biquad, and we could easily add more Laplacian biquads if we want to increase the roll-off of this filter, and so on.